So good afternoon, everyone. I'm Hao Huang, Assistant Professor of Social Sciences, and welcome to the Illinois Tech Social Sciences Great Problems, Great Minds Seminar Series. Before I introduce today's speaker, I would like you to know you can submit questions during the webinar by typing in the chat box. We will open the floor to questions at the end of the webinar. Now I will introduce today's speaker, Dr. Wenwen Zhang. Dr. Wenwen Zhang is a assistant professor of public informatics from Boston School of Planning and Public Policy at Rutgers University. Before joining Rutgers, she was an assistant professor of urban affairs and planning at Virginia Tech. Her research focuses on the social and policy impacts of emerging transportation technologies, such as automated vehicles, ride-hailing services, and micro-mobility. And leveraging data sciences and visualization techniques such as machine learning, natural language processing, and agent-based simulation to address critical urban planning issues. She has published more than 13 scholarly articles on these topics in top journals, such as Journal of Planning, Education, and Research, Transportation Research Part C, Emerging Technologies, Transportation Research we call the Journal of the Transportation Research Board. And also she has published more than 15 conference proceedings and a book chapter. She serves on editorial boards for Transportation Research Part D, Transport and Environment, and Transportations in Urban Data Science and Technology. Her research has been funded by NIH, Jeffries Foundation, and so on. She received her PhD from Georgia Tech School of City and Regional Planning. She has earned a master's in City and Regional Planning, Civil Engineering, and Computational Science and Engineering from Georgia Tech. It's very delightful to welcome Dr. Wenwen Zhang.
Okay. Yeah, thank you, Hao, for the great introduction. And today I'm going to just present a preliminary study that we have been conducted to explore the impact of perceived travel environment on e-scooter riders' stress levels. So this is some exploratory study that we have been conducted so far. And it is actually a part of the greater project that I work on. It's a large project team. The project is currently funded by the NSF SCC program. So you can see faculties from different domains like computer science, urban planning, engineering are grouped together to discuss how to actually make the micromobility, this emerging transportation, smarter and safer. So currently we're in, the major motivation of this project is to examine how do we examine the, do we increase the quality and quantity of data, pedestrian and micromobility risk, because so far there are not too many good data set existing on these domains. And also what factors increase the risk of those vulnerable users, especially in the context of near misses conflict. And how do we drive vulnerable road user fatalities to zero for all road users using connected technologies? So the project that I conducted is kind of an add-on to these questions where we want to understand how these vulnerable road users, especially the micromobility riders, are actually perceive the environment, and then in return, how does it affect their stress levels while riding on those e-scooters. And we're doing different kind of experiments in different cities, and so far we have the project that I'm involved in is in the Asbury Park, that is in the middle of the New Jersey. It's near the beach area. And this year, the PI, Dr. Clint Andrews, has just provided the lightning talks at the SCC program. So if you're interested, you can go to this link and then check out what the overall progress for the entire project is. And for the greater project, we're in towards the end of it, where we're doing this technical urbanism experiment in Asbury Park. And that's where this study takes place. So what this experiment we did is that we set up a pop-up bike lane at Asbury Park. So here you can see this is the intersection of the Kings Avenue and Cookman Avenue with the Asbury Avenue. So the green lines indicates where we put up the pop-up bike lane. And we want to, ideally, we want to see how people's perception before installing those bike lanes and after installing those bike lanes change, especially for e-scooter riders. And if you don't know about the Asbury Park city, it's a quite a small city with 15,000 population in 2020, and it's around 1.6 square miles. It's located in the middle of the New Jersey area here, and exactly in the middle of that county as well. So this is exactly the shore, the beach where it is located. So as you can see, it's a definitely a tourist destination because it has boardwalk. It attracts a lot of tourists during the beach season. And as part of the larger project, we have this studio where we install the pop-up bike lane. And Leanne and Hannah and Sean, they're the advisor of this studio, and where they lead a team of great students to put up those bike lanes where they have to do measurements and then do the painting. And we bought the utensils to set up a pop-up bike lane temporary for 1 week. And those paints will eventually removed naturally by itself. So the objective of this study is to see how e-scooter riders perceive their travel environment using the biometric sensors after this pop-up bike lane is installed. So for example, we want to explore what have they paid attention to, and travelers focusing on objects that are found to be associated with incidents like in the past, people have identified like bad pavements and crackers on the road. It tends to be dangerous for e-scooter riders. And what are the head turning movement patterns for the e-scooter riders? So for example, whether they are doing the shoulder checking to check out the surrounding environment when they're changing lanes, crossing intersections. And also the second research question is there any association between the perceived travel environment and travel stress level? So, and to be honest, these questions haven't been fully examined in this study. So as a part of this study, we're just setting up the equipment to explore the feasibility of using biometric sensors. And because it's very time consuming to collect even one sample of the data, because the people have to, that participant have to travel to that area, and then we need to calibrate the sensor, and he or she actually have to go around the pre-designed route to collect all these data. So I just, in this presentation, I just want to demonstrate how this technology can be used and integrated. So here is the writing experiment we did. So here, if you remember, this area is where the pop-up bike lane is set up. And here is the starting point of this e-scooter riding route. So the participant will travel along this route 3 times, and each loop is about 5 minutes in total. And Hannah, the instructor of the studio, she's brave enough to participate as the guinea pig for the experiment. So we set her up with the eye tracking glass and the stress sensor, and she rode this e-scooter along this route 3 times to collect the data. And on the top of her head is 360-degree camera, which helps to capture the surrounding traffic environment for us. But we are not there yet to analyze this data yet. So we're focusing on the data that is collected by the eye tracker and the stress sensor. So first, let's take a look at the eye tracking glass. So the equipment we used is a glass called Tobii Eye Tracking Glass 3. So this glass, advantage of this glass is that it captures both the position of the eyes as well as the pupil dilation. So there are 4 small cameras here at the bottom of the glass, as well as, I believe, 16 illuminators surrounding there. So those small videos tends to track where the eye position is, and then the illuminators tend to track the pupil dilation. And here is a front-facing video so that we will know what is the world view before this viewer, so that we can project where eye has been looking at onto this world view camera video. And it also has embedded a sound tracker to record the surrounding sound. And it also has gyro sensors, I believe, attached here and here to measure the head turning and tilting movements. And the sensor is fairly accurate for this pair of glass. The accuracy is about 0.2 degrees, which is considered as very high on the market. So before the users start to do the experiment, we just need 1 point on calibration to calibrate where the eye is. So the sensor kind of have a self-correction algorithm to track the pupil movement. Okay, and when we check get the eye tracking data, the analysis we have been conducted so far is the fixation analysis and the AOI analysis. And the fixation analysis is basically looking at where the eyes have been relatively still and holding the central kind of vision in place so that the visual system can actually take in detailed information about what is perceived by the human being. And this is because when we are traveling around, most of the time sometimes we're not actually looking at things and taking in the information. We're just browsing around because we can't just walk and then close our eyes. Sometimes we're just not paying attention. But there is a algorithm like the Tobii Pro Lab provides that can help us to capture where the eyes has been fixated at. And there's a larger chance that the information perceived by the eye is actually processed by our brain. And the second analysis is called area of interest. So it overlays the fixation point with the front view video, where we're trying to understand what kind of object that the eyes has been fixated on. So that's called the AOI. And other things we are planning on to study includes the pupil dilation, which is also a measurement of attention, and also head movement to determine shoulder checks. But for this presentation, I'll just focusing on the first 2. So here is a video showing what the eye tracking results look like. So you can see in the middle, the red point is basically the fixation point that the software detected using the eye tracking glass. And the lines between the dots indicates how eyes has been moved, and it is believed that it's called a saccade, that is something just moving the pupil and not paying attention to it. So as you can see, the rider is tracking the environment while trying to make a left turn to the other road. So she has been focusing on this car. And once this is passed, and she keeps on moving and navigating. So as you can see, it fairly accurately captures the eye attention, the tracking glass. But we noticed that during the experiment and also talking to people working at the tracking glass company, we realized that there are some limitations regarding this data collection. So for example, the pupil dilation can not only influenced by whether you are paying attention, it's quite stable for indoor analysis, but for outdoor analysis, it can also be influenced by the direction of the sun, because if you are looking into the sun, then your pupil dilation will be smaller. And also, the tracking rate drops once the rider moves towards the sun. Although you can see that we have the sunglass shade put on this glass, but sometimes when the rider is moving towards the sun, the tracking rate isn't very great. And the glass only works for people who don't need a glass or can wear eye contacts while traveling. So this is also one of the limitations of this glass. Okay, so this is just one right of it. And I think if I move on to so here we can see this is where we put up the pop-up bike lane. So she's traveling around it on it with cones separating the bike lane from the major environment. Okay. And so we look at the fixation result and separated the road into 3 different kind of environment. One is signalized intersection, the second is non-signalized intersection, and the last one is the road segment, just normal travel. We find that when in the more relaxed travel environment, for example, in the road segment, when there isn't many traffic on the day we collect the data, the average length of fixation is actually longer. So the average is 212 milliseconds, while it is shorter in the signalized intersection, which is around 200 milliseconds. If it becomes non-signalized intersection, where the rider has to frequently turning the head and switch on to different things, then the fixation duration kind of becomes shorter. So it becomes 180 milliseconds. So as you can see that the busier the environment is, the fixation period actually becomes shorter. And traditionally, when we want to analyze the area of interest, it's a very tedious manual labor process. So for example, so if you want to analyze for how many seconds, half percent of the time the rider has been focusing on vans or other type of cars, the student or a researcher have to go through the video frame by frame to label. So for example, this is a van, and the next frame, this is also a van, and then aggregate the data up. So as you can see, it's very time consuming, and that also limits the type of objects that we want to understand the writer has been focusing on. But recently, with the advancement in the computer vision, we can automate the process. And the algorithm we selected is called PSPNet. It automatically detects a lot of objects on in the street by doing the image segmentation. So changing from this input image and output this final prediction. So for example, this is traffic light, this is people, this is sidewalk, and the background is a building, so on and so forth, so that we can just overlay the focus point with this segmentation result to directly automatically extract the AOI data out of the raw data. So what we have been conducted is that we first convert the video into frame-based images and use the PSPNet algorithm to segment the images automatically into different road objects. So for example, this is a frame from our image, and correspondingly it is segmented into different type of objects, for example, sky, traffic light, cars, so on and so forth. And by overlaying it with a small radius of a fixation point, we find that over 93% of the time, the rider is focusing on road or traffic related objects like the sidewalk, pavement, other moving objects like car, van, truck, pedestrians, or infrastructures like street light, traffic light, signboard, or some even amenity kind of objects on the road like trees, bushes, etc. So currently we're still doing literature review to understand what should be considered as the point of focus, because we only know exactly the center of the fixation point, but sometimes the brain can process peripheral eyesight as well. So we're still conducting literature review to see what is a robust buffer for this capture area to calibrate this data. And also I just want to mention that PSPNet is trained based on multiple data sets, but it's fairly accurate, but not like perfect. So for the segmented image, some physical objects can be better detected. For example, person, cars, and road, sidewalk, they are fairly accurate. But once it turns to, like, for example, truck, it turns to the traffic light, then the accuracy drops. And it's also fairly accurate in detecting trees, plants, so on and so forth. So that's why we don't want to report like for what percentage of time that it has been focusing on each type of these objects, because it could be a misclassification in some cases. So what we did is that in certain environment, we just group them together. So for road users, it includes like car, truck, bus, pedestrians, person, bicycle, those road users. And then we have the infrastructure based, like the furniture, signage, those static things. And we also have amenity kind of features like plant, trees, bushes, those vegetations. And when we look at it, it seems that at signalized intersection, in most cases, anywhere around the road, HANA has been focusing on the infrastructure kind of objects for most of the time, while at the signalized intersection and non-signalized intersection, she tends to focus more on the road users, other road users, and that's kind of reasonable because she's trying to cross the road, right? So especially in the non-signalized one, and when in the more relaxing environment, she kind of observe more amenity type of objects in general. So our next step is to overlay this eye tracking data with the LiDAR data points that we have been collected using this van in Asbury Park, so that we don't only do this kind of 2D analysis, but also convert it into a 3D analysis to see how the riders actually perceive different objects in what sequence and in kind of distance order, to understand how they navigate the environment. And the second part is the stress level data collection. The sensor we used is called galvanic skin response sensor, GSR sensor. It's a sensor that people can wear on the hand. So there are two sensors that attach to us to our finger to detect the skin, the sweat gland activity that reflects the intensity of your emotional state. And this sensor is frequently used to measure stress levels in the existing literature. So we have one equipped with HANA, and this is the result for the last ride she has in the field. And so we try to label it manually by cross-watching the videos and then checking the timestamp collected by this sensor. And this one captures our attention, and it's because So here the green part is where she ride on the pop-up bike lane. And towards the end of the ride, she almost fell from the e-scooter, and which peaked the GSR data and then continued to climb until the end of the experiment. So which is kind of reflects that this sensor can, to some extent, robustly capture the stress level of the riders, although the rest of the trip is fairly smooth without too much waves there. But whenever she's entered an intersection, especially the stop sign kind of busy intersection, the stress level will go up a little bit because she's checking the environment. And we find that the limitation of using this sensor in the field is that the weather condition matters a lot because it's trying to detect the sweat gland activity. So if it's very hot and then the rider is sweating a lot, then it's going to influence the reading. And noises can also be introduced if the person is frequently doing the hand gesture and there are a lot of turbulations on the road. And so our next step is to pair it with a heart rate tracker to remove possible biases. And we're also planning to do the post-ride survey to get riders' perceived stress level more accurately based on their memory writings through this experiment route. So here is a synchronized eye tracking and GSR data where Hannah almost fell. So here she is, yeah, as you can hear that she braked too hard and almost fell because the light is changing the signal, and then she actually ran a red light, so which makes the GSR reading even higher until she get back to the destination. And actually, one of the bottleneck of this project is also synchronizing data from sensors that data collected from different sensors, because each sensor collects data at a different frequency, and also the way they do the time stamping on different sensor are different. So making it very hard to synchronize or merge the data from the two sensors together. So somehow we, in this initial experiment, we finally had kind of a robust algorithm to synchronize the two data, at least from these two sensor tracks together. And so our next analysis is future steps, I would say, is to develop a more comprehensive analysis framework, including doing more in-depth eye tracking and GSR data analysis. So as you can see, the data that we have been analysis so far is kind of preliminary, and we only have one sample so far collected. So the next step is to see what other metrics we can incorporate into this analysis framework. And also the stress data is actually very hard to measure. So we're planning to add in alternative stress data quality control method, like adding a Garmin watch to track the heart rate, and also post-riding survey to do the data quality control. And we're also trying to add in a near-miss sensor into the experiment. So currently, I am working with a company called No Rock, where they have a device to be put on the either the bicycle or e-scooter to measure how close the vehicle has been traveling to your side, and give out warnings, etc. And the last is what we really want to do as the next step is that once we have all those data collected, we want to see whether there are associations between what has been perceived from using the eye tracking data versus the stress level of the rider, so that we can see what built environment features will actually influence how comfortable the riders use those infrastructures. And we're also launching more data collection, definitely, because here we just had one demo using the studio setting to collect the data. We only have one data point. And so we're adding in the heart rate tracker and collect more sample data on Rutgers campus. Currently, we're thinking about the College Avenue. So we have received seed funding from Rutgers internal grant to collect 30 samples of cyclist, pedestrian, and e-scooter rider data each, to have a much bigger data set so that we can at least do more statistic analysis to say whether, for example, fixation is really longer at signalized, non-signalized, shorter at non-signalized intersections, so on and so forth. With one sample, we can really do this. And so we have selected routes so far on Rutgers College Avenue, which breaks down into bike pedestrian only, or have separated bike lane here, and a mixed traffic, but with very light traffic volume or medium traffic volume or busy streets here, to see how their gaze eye tracking results actually differ by those environments and whether it influences their travel stress. And this environment has substantially, those roads has substantially different travel environment on the campus. And currently we're still in the stage of applying for IRB for this initial data collection effort. Hopefully it can be launched the next spring to finalize the data collection. Yeah, so here, that's all I have for today. And let's see if you have questions for this. Oh, I saw one question in the
Yeah,
in the
I
chat.
think Dr. Zhang gave a very interesting presentation about how the use the emerging technologies to explore the impact of perceived travel environment. So on the scooters, e-scooters stress level. So I think, yeah, I have one question from the chat box. Is about, did you also conduct some questionnaire survey?
Yes, we currently have a questionnaire survey, but in the Asbury Park, we didn't conduct because it's just one people and we work together forever. She just generally talked about how she feels along the road, and I know exactly what's the situation there. So we didn't do that survey for this person, but for the experiment that we're going to conduct here in the College Avenue, we have a post experiment survey asking people about 3 types of questions. One is their social demographic information, and the second is their level of experience with that mode. So for example, are they comfortable riding bikes or e-scooters, and for how many years they have ride, how many accidents in the past they have ride, and are they familiar with the route that we designed, so on and so forth. And then the third part is to ask about their stress levels while riding it by segment, and also asking them to rank the features that they think influence their stress levels the most, so that when we do study, we can pay special attention to the features that they have been, they claim to influence their travel experience. And we also have open-ended questions to ask them, like, how do they think the environment can be enhanced to have more relaxed travel experience, etc. Yeah.
Another question is from hi, Dr. Zhang, thank you for the inspiring talk. I wonder, where the sensors, the glass, the skin sensor themselves can affect your stress level. For example, some people may not like to wear glasses while cycling.
Right. That's a good point. It has been a criticism in the literature in the past, especially when the eye tracking sensors has been very heavy and it looks weird when people wear it. But with the advancement of this this device, especially they have to wear the sunglass on top of it. It's very hard for other people, first of all, to detect that that person is wearing a special glass, especially to collect the data. So some people feel more stressful when they do that. And also the weight of the glass has become so light. It is even lighter than the glass that I'm wearing right now. So I don't think it's like giving cyclists a lot of burden that it will influence what they look at on the road, etc. And in terms of stress level comparison, we're comparing traveling in different environment, how it affects stress level, not comparing like whether they're just travel casually versus doing this experiment, whether they're becoming more stressful or not. And as a matter of fact, it is very hard even for the same person to determine whether stress level go up for the same person to travel on the same route on different days, because the GSR readings are just not that reliable for cross-day comparison. So if we're just comparing segment by segment to see how the stress level varies using the glass, I don't think it's going to bias the result that much. Yes, they may be feeling uncomfortable, but they are feeling uncomfortable throughout the entire route. And when we recruit those volunteers, we will give them the chance to warm up the ride in the parking lot first before they decide whether they're comfortable enough to go on the road to actually collect the data. If they don't feel comfortable, they can just leave and not participate in the field experiment.
The other question is it possible to separate the still and moving objects in built environment using the eye tracking data?
Can you explain like what are you trying to achieve like by separating?
So Funong Wang, could you elaborate your question?
Okay, I mean, for example, when you're using the eye tracking data, I think there are some findings suggesting that people may pay more attention to the moving objects or the changing environment because it usually means more risks or some other attracting their attention. So I think if we if especially when we related this data to stress level, I think the moving objects may have more sense. So I think is it possible to separate the moving objects like cars and bicycles or some other objects from the some still objects like the buildings and like the green views, etc. Yeah.
Okay. So mostly we're currently using this image segmentation algorithm to do it at this stage. So one thing we can roughly do is that we can definitely separate bicycle, cars from other objects like sidewalk, trees, and by common sense that we know trees sometimes will move because of wind, but it won't really be like moving objects on the road, and so are the buildings. What is very tricky to separate is whether, for example, that a cyclist is actually moving versus not moving, because we don't have all I have is the real world view cam video data, and then the cyclist or the e-scooter rider is also moving. So it's very hard to determine based on the video whether, like from human perspective, we know whether that the other e-scooter rider is moving or not. But from the image segmentation perspective, it's very hard to determine because both could be, one could be still, the other could be moving. So it's very hard. But however, with if we have enough funding to equip this rider with LiDAR sensors, then that's another story. We can actually detect the distance between different objects to decide whether they're moving, and we know the speed of the current rider to detect whether it's a moving truck versus a stopped car on the curbside. But with the current technology we have, I think it's very hard unless we hire armies of students to label it for us. Yeah.
Okay.
So that's a very good point.
So, and also I have a question is about like you mentioned like the eye tracking glass for the dilations. So how actually accurate? So since you mentioned it could be affected by some like the outside environment, like the sun. So how accurate actually for the dilation? And also could affect the results. Your
Yes.
results.
So that there are two solutions to the bias problem. One is that we use an additional illuminating sensor to offset the light that the rider receives from the environment to control for the baseline lighting, which we didn't do. And the other kind of strategy is to not compare eye dilation data between different segments, but just focusing on one specific segment where the sunlight is fairly stable because it's traveling to the same direction towards the sun, and then to understand the variation in the dilation and then overlay it with fixation data. That's, I think, the approach that we're going to test out to see whether it works or not, because we believe that on certain segment of the road, if the road is not like heavily shaded or have like changes in the height of the building, the lighting situation should be similar if he or she is traveling straight, right? But we still need to test it out before I want to do like confirm the statement regarding, oh, this is how it is done. Yeah.
So then it's possible for the relative like sun shade or this kind of data to integrate it to this data sets.
Right. It can be integrated if you have a illuminating sensor separate from the eye tracking glass. So to detect, for example, you can add on one more sensor to the eye tracker to detect what is the illumination point from the environment.
Oh, so which means for all those sensors actually, you can add it by yourself.
Right, you can keep adding sensors too. It's just going to be harder to pass IRB.
Oh,
you're collecting whole lot more data. So you can add LiDAR sensor, you can add, for example, acceleration sensor, speed sensor, all those things. But the more sensor you add, it's just harder to synchronize the data, because the tricky point is that you cannot start all the sensors at the same time because they come from different manufacturers. And all you can do, the trick I learned is that first start your eye tracking sensor and ask the respondent to look at all the other sensors when you started, so that you have some references point to actually calibrate your data. Because some sensors come with Unix time, some sensor comes with local time, some sensor comes with, other time zones.
Yes.
Yeah, it's very hard to synchronize.
That's very interesting. So can I ask another question? You mentioned that in the future it will have more participants. I wonder, do you want to ask them ride together around the same time to simulate the flock impacts or riding separately?
Currently, the plan is no. That it's because of two reasons. One is we only have two eye tracking glass for the research group, and each eye tracking glass is 20K. So it's very expensive, and so it's very hard to scale it up. And also the currently we're only want to examining that how one cyclist or e-scooter rider is perceived the environment. Although like for e-scooter riders, it's also observed frequently that they travel in flocks because it's a tourist destination thing. People group around and then travel around. And that's definitely something that worth exploring, but currently we're not examining those kind of things under the current lab setting, I would say. Yeah.
And then also, I'm wondering, and since you mentioned actually the how you analyze the image based on the user like a classification, so then you show that the results is actually for different objects has different accuracy for this image classification. Right. So, so what factors usually determines this different objects accuracy?
I think I'm not really sure how it could be depending on the training data, because the PSP net, for example, the currently one that we're using is trained using the skyscraper. It's called skyscraper data set, which is prepared by the MIT. So if you have a larger data set and a more Google Street View kind of data set with correct labels, you can potentially increase those accuracies. And even if, like, for example, the bus accuracy, truck accuracy is lower, but if you group them together and have a category called truck or bus, then the accuracy could be significantly improved, because the confusion matrix looks like they're confusing one versus the other because they look similar to some extent. They're bulky, the speed is lower. To some extent is like that. So that's why in the analysis, we didn't do specific type of object analysis. We try to group things together to understand what is the percentage of the time that has been allocated in each category, trying to avoid, for example, the misclassification in this sense. But still, I wouldn't say it's 100% accurate. Yeah.
I see. And also, just now you just mentioned the fixation results. Could you explain that? I think for you have different percentage for this, which means it's showing like they have different like fixedness object by different like the road type situation. I think one is like a singularized intersection, and one is a non-singularized intersection, and one is just the road segment. So how actually this will be for these three types of like road users, infrastructure, and amenity will different or varies between these three different environment travel environments.
You mean how the users act differently in these three environments?
Yeah.
Yeah, so we're trying to that's what we're trying to understand, whether they're focusing on different type of objects in this different environment, or whether they do head movement the same frequency in those three different type of environment or not. So the separation of those environment is a human labeling. So in the Tobii Pro Lab, we have like event creation where we can segment the segment of the video, saying that, oh, here she entered signalized intersection and where she left the signalized intersection. So that part is still like manually inserted, divided, but the rest of it is like purely automatic using algorithms to detect what percent of the time they have been focusing on what using the eye tracking result and image segmentation result.
Then how do you think these results will be actually have some like policy implications for the urban planning?
It's currently purely descriptive. The eventual goal is to look at whether more experienced riders pay what kind of attention at different situations, and whether that influence their stress levels. And if certain area, like let's say, if I put in a separated bike lane, it significantly reduce the stress level, that's a policy implication to road designers, saying that instead of have separate only a mixed traffic bicycle lane, we should really put in a separated bike lane because it significantly reduce their stress level and increase their comfort level. But currently there's no such literature to support such a statement. People are just still arguing whether just I paint a bike lane on the road versus I really have separated dividers between them will make a difference or not.
Okay, so which means it's may a promising research topic to do in the future. For
Right. I see another question. So I only have 2 minutes left. I really have to go. The visualization, in addition to analysis, do you have any plan ideas for visualization purpose? And the data look very interesting and might be good for public engagement purpose. And yes, these are both on the agenda. So ideally, we want to visualize visualize the objects that the rider has been focusing on using this 3D environment, so that we know when they travel along the street, how they perceive the environment along the street. And also we want to integrate this with studio settings to help local people to understand what they have really pay attention to their infrastructures while navigating their neighborhood, which is integrated with an urban design. Hopefully to be integrated into an urban design studio, because so far those design kind of thing is like purely separated from the academic modeling part of the team. So that's what we really want to do.
So I have another question. What does the high level of stress mean for the real world? Is an indicator to be controlled or reduced for policymakers?
Actually, we don't want. So there are debates regarding the stress level. The goal is not to say we should like make those people less stressful while riding on the road or so on and so forth. The goal is to make them comfortable riding on the road while maintain certain stress level, because certain mediate, even high stress level actually means that you are alert to the road conditions. So we don't want people to be fully relaxed on the road and hey, I'm not paying attention to anything and I'm kind of putting them in danger. We want them to be alert, but we don't want them to be very uncomfortable to ride. That's a different thing. So the goal is not to reduce the stress level, but to put in infrastructure so that they can travel more comfortably. Yeah. Okay.
Okay. Usually we give thank you Dr. Zhang's great presentation. We give the speaker the applause to great presentation. Thank you so much for giving us such a great presentation to let us how to these emerging technologies affect the policymakers' views and the decisions help. So.
Okay, yeah, I really appreciate the opportunity. It's a great fun presenting to the group, and I receive a lot of good feedbacks as well. Yeah.
Okay, thank you.
Thanks.